Let me go over one of the homework problems where there's a combination of product rule and chain rule. So this is number 29 from your homework. So we see that, I mean, we could get away without having to go through product rule and chain rule. I mean, you could FOIL all this out, but we really want to practice our ability to use product rule and chain rule. So we see that there's product rule involved because there's two separate terms that are two separate parentheses that are being multiplied together. So that's where the product rule comes in. And we're also going to apply chain rule because each of these are raised to different powers. Now I could fold this out and avoid chain rule, but I'm just going to go through chain rule because I can treat each as a function within a function. So for instance, this 2x cubed minus 1 cubed is really parentheses cubed and 2x cubed minus 1. So let me just kind of go through each of the derivatives here. So f prime, I'm going to leave it in this form. So there's an outside inside portion. I got parentheses squared and as the outside and inside being x squared plus 4. So my outside derivative is just 2 parentheses to the first power times the inside function's derivative, which is 2x. So that takes care of f prime. G function, no changes. F function, no changes. And then G prime of my product rule, I go back up to G, recognize the need for chain rule. Parentheses cubed is my outside. Inside is 2x cubed minus 1. So outside's derivative, 3 parentheses squared. Inside's derivative is 6x squared. Any questions with that so far? Now, you can leave your answer in this form, but it is a good skill to be able to factor further into this problem. And the way that you can factor without having to expand everything out and put everything back together is well, what I did first was I just try to clean up my individual space. So from here, I got to this section here. Now, if I can look at these and just find what is common between these two, then that can speed up our factoring process because whatever is shared between these two, I can just pull out and then I can combine the rest a lot faster. So for instance, between these two expressions that I have highlighted, there's a shared 2 between 4 and 18. There's a shared x between x and x squared. There's a shared set of parentheses, x squared plus 4 to the first power, and I can take 2 of the 2x cubed minus 1 squared out. And if I can take all that out, then all the leftover can be in its own bracket or parentheses, and then that will allow things to clean up a lot faster. It's a lot easier to merge these together with all the factors being pulled out. So, so that's factored form. That is the same as this, but it's useful to know how to get to this part of the problem quickly. Any other questions with homework that you want me to go over with you? Okay, next up we have implicit differentiation. So let's go to page 11. Okay, so we have something called explicit equation. So explicit equation is where your y is solely by itself, and all your x terms are separated. Your y's and x's are not mixed with each other. Basically, everything that we've done so far has been functions. Y is just by itself, and it's just to the first power. Implicit equation is where your y variable is kind of mixed into the equation. There's something done to the y variable that you're not used to seeing. So that may not look as familiar. So something like this, x minus y squared equals square root of y plus 5. So this is considered an implicit equation where your y is defined implicitly, and it's not explicit like this. Now, typically, implicit equations are not going to be functions. So they're not going to pass the vertical line test. So they could be graphs, you know, that looks like this, for instance, right? Obviously, it doesn't pass the vertical line test, but we can still find a slope formula for a curve that doesn't pass the vertical line test. So we can find slope formulas for functions. We can also find slopes for non-functions. It just requires a little bit. We just have to keep track of certain things a little bit more when we are doing these implicit equations. Sorry, give me 1 second here. So if I want to find the derivative of x with respect to x, it's just simply 1. So when we find derivative that has x's in them, you're just going to treat them the exact same way. There's not going to be any differences. So x squared derivative is just 2x. E to the 5x. Okay, so this is a little bit of chain rule. We'll talk about this. We learned how the derivative for e to the x is just e to the x. But if we have the derivative for e involving chain rule, then e to the u is just e to the u, the original function, times the exponent's derivative. So e to the 5x is just e to the 5x times 5x's derivative. That's the inside portion, so times 5. What's different about when you're trying to find the derivative if y is involved, you're going to find the derivative like you normally would, treat y like you would x, so the derivative of y would be what? Just 1. But we're asking for y's derivative with respect to x, so we're going to include a dy dx to indicate that this is a dependent variable, and we have to keep track of that new derivative variable there. Before, technically, there are derivatives that show up with the x's side, but they all go away because we're finding the derivative of x with respect to x. So that just washes out, and we never keep track of them because they're just always equal to 1. So that's why we never do it for the x's, because we're just finding the derivative with respect to itself, and there's not going to be anything that we need to worry about. So the big picture now is, if we ever want to find the derivative of a dependent variable like y, find the derivative, and then you're going to do dy over dx, or the derivative of the dependent variable over the derivative of the independent variable. Usually y is dependent, x is the y is the dependent, x is the independent, but we're going to move into some units where that may not always be the case. All right, what do you think y squared's derivative would be? Right, so we find the full derivative like we normally would. We follow the rule that we normally would, and then we should have to make sure we attach that derivative variable. Okay. E to the 5y would just be what? E to the 5y times 5 times the exponent's derivative. And because we're asking for y's derivative, we need that dy dx. So let's do a full example, and all the steps are spelled out. So we're just going to follow these steps. So whenever you have to do implicit differentiation, it should be noticeable that okay, anytime your y variable is not by itself, if it's mixed into the equation, if something is done to the y, if you see multiple y variables and something done to the y, you know that it's going to be implicit. So if the y is not by itself, we have to involve implicit. So step one, take the derivative. Each time the derivative of y is involved, include a dy dx after you find the derivative of that variable. So let's just go down the line here. Okay, every one of these are separated. We can just rely on power rule for each. There's no need for product, quotient, or chain. Okay, y squared becomes
2y.
good 2y dy dx minus we don't do anything special with x's. Technically dx over dx, but that just washes out. Okay, what's 3y's derivative? Good. So even though the y disappears, we are asking for y's derivative. 3y becomes 3, but we still need to include dy dx. Sometimes students forget that and they say, oh, the y is gone. There's nothing more that needs to be done. We need to include dy dx because we are asking for a variable that starts off with y. Next up, we're going to gather all the terms with dy dx on the left side, everything else on the right. So we have two terms that are include dy dx. So we're going to group them together, gather them together on the left side. They say left side, but you could do it on the right side as well. It's just typically we're more used to having the variable that we're trying to solve for on the left side, but it doesn't have to be. Next up, we're going to factor just the dy dx. Even if there are other common factors, we don't care. We only care about solving for dy dx. So just factor dy dx. And then finally, you're going to solve for your new derivative variable, which is dy dx. dy dx is another way of saying y prime. What do you notice about the derivative? That this is basically a derivative. Okay, so this derivative basically describes the slope behavior of whatever this graph looks like. What's different about the derivative function compared to other derivative that we've seen in the past? It has multiple variables. It has the potential for both the x and the y. And let me just kind of give you a reasoning as to why that's the case. Let's say I had a graph that looked like this, right? Obviously, it doesn't pass a vertical line test. And it could be an equation that could be defined in terms that involve y and y squared. The reason that you would need both the x and y is because let's say you had a point up here or down here and down here. And let's say this order pair was like 2, 8. And this order pair was 2, 5. And this order pair was, 2, 1. The reason why the derivative needs the x and the y value is because if you only give it the x value, then the derivative it needs more information, right, guys? So if I say, oh, I want to find the derivative at x equals 2, it's not going to know which one you're talking about. You're talking about this slope, or this slope, or this slope, right? They're all different slopes at different points. So that's why it needs both the x and y value, because there's that chance that you have points that are overlapping each other, and it needs additional information so that it actually knows, okay, you're talking about this point. Okay, great. I can give you the slope at that point. So that's why your derivative needs additional information, because there's a chance that graph overlaps each other. It needs both the x and y to pinpoint the slope that you want. Okay, any questions about the steps? All right, you guys want to try number one? Go through that process. Pretty much the same as what we did above. No messy rule, just power rule. Let's just see how comfortable we are with that process. Okay, if you get done with one, try number two. Number two, there is a need for chain and product. Okay, so I'll be right back.
That's what you get. Yeah. Is it? Nope.
Go ahead.
What do you start with? Implicit product or chain? Like what's this? You know what? I'll just wait till it comes out. I did number one. That's good. I'm parched.
I'm just making stuff up for number two. I'm making my own math rules.
It's especially more than.
Number one.
But then they do both the ones left.
Yeah, okay.
I always just want to balance my brain. All right, I don't know what's going on. Coast. Dy dx over or times 4x3 plus 2 over 3 minus 2 minus. What did you
That's so. That's.
You have to bring it over one side.
Yeah.
What did you do?
I just made stuff up for number two. I made up my own. My method for number two.
Girl. Are you starting with power?
Yeah, this.
Yeah, I don't know what I'm doing. I did. I got coast x y dy over dx equal 10.
It looks like the other one worked. Alright, not.
All right, how do we do with number one?
Cool.
So power rule. Here's something that I want to point out, that however many y's you see in your equation is how many dy dx's will pop up. So we see two different instances of y variable. You'd be expecting two dy dx to pop up. I think sometimes the mistake that I see with implicit is students would include dy dx whenever there's a y left over in the derivative, which is not always the case, right? Because there's two y, the y disappears, but we still need a dy dx because we're beginning. If you're beginning with y and you're asking for y's derivative, you need to include that dy dx. Okay, let's talk about everybody good with one? All right, let's look at number two. All right, sine of xy equals 10x. We see that there's a function within a function here, right? That xy is inside that sine function. So I'm going to start off by identifying that on the left side, at least, there's an outside portion and there's an inside portion. Outside, we can just go through a derivative for sine, but the inside, we got to go through what for this piece? Product rule. Okay, so let's do it. Let's build it one piece at a time. So first, outside's derivative, sine's derivative is just cosine. Now, when we find the derivative of outside portion, do we make any changes to what's inside the parentheses? Not yet. Okay, so cosine of xy times, now we're ready for the whole product rule that's going to come out of that xy. So I'm going to kind of make sure we build it out here. This is f prime times g plus f g prime. All right, so let's do this here. I'm going to treat x as my f. I'll treat y as my g. What's f prime? G doesn't change, just y. Back to f, doesn't change, just x. What's y's derivative? Good, y dx. Equals, good, 10. You only see one y variable, so we're expecting one dy dx, and that's what happens. Now, we're just trying to solve for dy dx, but dy dx is kind of stuck inside this bracket. We're going to take that cosine xy. We're going to distribute it through, and that way we can free up this term, and then we can eventually move towards solving that dy dx. We're going to subtract that y cosine xy over, and then that way I'm down to just dy dx term, and I can divide that rest over. Okay, any questions there?
Yeah, I did some like different steps of letting go with me. Slightly, that's why I'm asking. I didn't distribute, I just divided by cosine x by both sides and then subtracted y and then divided the whole thing by x.
That's fine. You're left with a more complex fraction, right? That's fine. It's just if it's a multiple choice question and your answer choice looks like that, are you able to get to that? That's the question. So as long as you know that, oh, I can maybe go down a different path, that's fine then.
Yeah, I like know how to think.
Yeah. Okay.
Yeah.
But yeah, technically that works. You found a way to get dy dx by itself. All right, next page. All right, so first things first, it says find the equation of all tangent lines for x squared plus y squared equals 4 at x equals 1. Let's first build the derivative first. We know that there is a need for implicit because why? You see y, something done to the y's, right? And the y is not by itself. How many tangent lines are we expecting? 2, right? So you can imagine that x equals 1, that there's going to be 2 different locations, and you're going to get 2 different slopes, 2 different points, 2 different tangent line equations, right? So let's go ahead and find our derivative. And then we'll see if the function and derivative will give us enough information to build those tangent lines. Careful here. What does that 4 turn into? 0. Yeah. I think sometimes we feel like, oh, we're just taking the derivative of the left side, and they make that constant immune to the derivative, and they leave it as 4. So just make sure that both sides is impacted by your derivative process. That constant will not stay that number. It'll turn into a 0. Okay, I'm gonna plug one into the function or into the equation now to figure out what the order pair is. And then once I get my order pair, I can put it into my slope formula to get my slope and then point in the point slope form. What's gonna happen though if I plug one in for x? I'll get y squared equals 4. Yeah, and so that's good, right? That we are able to get two different y values because we're expecting two different order pairs. So what are the two order pairs that we're going to be working with? 1, 2, and 1, -2. So each point will tell us a different slope.
Shay,
Y squared equals 3. Oh, sorry. Thanks. I forgot that. My mistake. So how can I find the slope at each of these individual points? Like dy dx, right? And this is why they need both the x and y, because you have points above each other. They need the y value so they actually can know which point they're talking about. Okay, try that. See if you can. So at order pair 1 root 3, my slope is -1 over root 3. You don't have to rationalize the denominator. You can leave it radical in the denominator. Second order pair 1 comma negative root 3. My slope there is going to be 1 over root 3. And so I have two equations, two tangent line equations, one for each point on the graph where x equals 1. Sometimes when your derivative have both the numerator and denominator, you may be asked to find vertical and horizontal tangent lines. So a horizontal tangent line is simply what we've been doing in the past is, because we know that whenever we look for slope 0, we're just saying our derivative equal to 0 and then find that x value, right? But if there is a numerator and denominator, the numerator, if I set the numerator equal to 0, that's going to tell me the location where the graph is going to experience slope 0, horizontal tangent. But if there is a place where the slope does not exist, such as a vertical tangent, I can find the location of vertical tangents by setting the denominator of the derivative equal to 0, if there's one that exists. So a good example would be a circle or an ellipse that has both horizontal tangents and vertical tangents. So we're going to try that with number 4. Number 4 and 5, we're going to find the derivative, build the derivative, set the numerator equal to 0 to find horizontal tangents, and then set the denominator equal to 0 to find the lines where vertical tangents exist. Okay, let's try that. So number 4, start off by building the derivative equation. So once I have my derivative, I take whatever is in the numerator, set that equal to 0. And I can find an x value location for my horizontal tangent. Now that I have my horizontal tangent location, how can I find the actual lines? Plug it back into the original equation, right, and find the y value. Same equation as number 4. We can just start off with dy dx. Vertical tangent. Set the denominator equal to 0 to find the location or a partial location of your vertical tangent. And once you have that partial information, plug it back into the original equation to get that full set of information you're looking for. Yeah, that's fine. So imagine this ellipse here where you have 2 horizontal tangents and 2 vertical tangents. So this upper line will be y equals 2 root 2. This bottom line will be y equals negative 2 root 2. This vertical line on the right will be x equals 4 over root 3. And this vertical tangent line will be x equals negative 4 over root 3. Let's see. Maybe we have time for do 1 or 2 more. Let's go to page 14. Let's try number 14 on page 14. Find the slope of the tangent line at a given point. So go ahead and build your derivative first. Once you find your derivative, your dy dx, then you can plug negative 1, 1 in to find the slope. But let's talk about what process is needed if to do the derivative. Product rule. Okay, what else? You see a bunch of, you see y's mixed into the equation, right? So implicit as well. there's some notation because whenever if we're just trying to find the slope at a point, usually it's a function and it's like f prime of -1, right? And because there's only one variable to plug in. Typically the notation, if there's multiple order pairs that's required for the derivative, typically to indicate that you're ready to plug in that order pair into the derivative to get the slope. The notation is this dy dx, and then you put a vertical line, and then you put order pair. So this indicates that I want to find the derivative at a point. It just feels more, it feels a little bit awkward because you got that two numbers that you got to indicate that you want to plug in. So this is typically the notation that they use, or that's used to indicate, oh, I need I need both the x and y value because the derivative requires both variables. Okay, final one I want you to try. Page 15, number 20. Page 15, number 20. So first find the derivative. You're going to need chain, product, implicit. It says slope of the normal line, but go ahead and find your derivative. Find your slope. Once you get to your slope, then you can get that slope to the perpendicular slope, right? Which is the opposite reciprocal. So do the tangent line slope first, and then flip it to get the reciprocal.
Or 20.
Yeah, number 20. Yeah, page 15.